Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Aiman Bahmat Shukri alias Pakuitan. Note metric is AE180045. My supervisor is Prof. Madya IR Dr. Irwan bin Sulaiman. I will present my final year project. My title is Electromagnetic Performance of Cemented Stator Flux Switching Permanent Magnet Motor. Introduction. Flux switching permanent magnet machine is a brushless machine of stator type permanent magnet machine. Cemented stator flux switching permanent magnet machine is electrical machine with two or more cemented stator parts separate. Advantage of FSPM is high torque density, good thermal management, low magnetization, and suitable for high-speed application. This research will focus the design structure and performance of flux switching per magnet cemented stator and conventional stator. Problem statement. Conventional flux switching per magnet machine have many advantages. It also have certain downside. The downside is flux linkage, longer flux path, and drop performance at starter part where one of the starter cord is broken down. This project proposed to invention of cemented stator (FSPM), which can increase the flexibility of starter cord and will focus the issue electromagnetic performance. There are three objectives of this project. Number one is to design the cemented stator flux switching permanent magnet flux FSPM. Second is to analyze the electromagnetic performance of cemented stator FSPM on the issue relating to the stator segmentation technique. Number three, to compare the electromagnetic performance of conventional and cemented stator FSPM. The operation principle FSPM. I will explain the basic operation. The flat winding cord is fed with direct current continuous while the armature winding supply DC according to the position of the rotor. Flux enter from starter pole through the rotor pole and exit aligned starter as shown in figure A. You can see in figure A, this is flux will enter from starter to the rotor. At the same time, with the magnet having constant direct current, the polarity of armature coil turns to receive the direct current F plus A minus by switching the flux enter from rotor pole to the starter pole and exit aligned rotor as shown in figure B. And you can see that in figure A, you can see the stator flux enter from stator through the rotor, but in figure B, we'll be switching flux enter rotor through the starter, exit to rotor back. That basic principle of flux switching permanent magnet. There are three designs in this project. First is conventional flux switching permanent magnet. I choose 12 slot and 14 pole. For cemented flux switching permanent magnet, there are two designs, 2 cemented and 4 cemented. For 2 cemented, I choose 12 slot, 10 pole. For the 4 cemented, I choose 12 slot, 14 pole. Why the 2 cemented is different in number of rotor? Because 12 slot, 14 pole is not suitable for 3-phase motor. For the methodology, after we finish the design circle using geometry editor, simulate using geomet designer. So we have no load analysis and load analysis. For no load analysis, we have 12 coil arrangement test. After that, we go to 3 coil arrangement test, and after that we go to UV test, and if coil flux and torque graph show the correct waveform, we go to zero to position, back EF, coil flux linkage, cogging torque. If not, check circuit or coil setting, and we go to back to 12 coil arrangement test. For load analysis, after we finish no load analysis, we can calculate the value of armature current density JA, and insert the value of JA. We run the analysis and we can produce coil flux linkage and cogging torque. If coil flux and torque graph show the correct waveform, we can proceed to torque vs speed vs power. And if not, check no load analysis graph and coil setting, and go back to insert the value of JA. For the result analysis, we have 12 coil arrangement tests, and in this analysis, we run the simulation and we must get the circuit like the waveform like this. After that, we see the most same pattern, and we can arrange it to become 3 coil tests. In 2 method and 4 method, the pattern is not same, but we take the close pattern and we combine to become 3 coil test. After we get like this, and we go to UVW test. In UVW test, we using the 3-phase circuit. We run the simulation and we got like this. For zero to position, the zero to position is important because we want the U flux waveform in the center. As you can see in UVW test, U flux waveform is not the center, so we must adjust the rotor, adjust the degree of rotor to make it center like this. And this is the result for zero to position. For cogging torque of all design, after we finish the zero to position, we can produce the cogging torque. For no load analysis, you see we compare the all design. As you can see in the design, 2 segmented flux switching permanent magnet motor have highest torque, and followed by 4 segmented stator, and lastly the lowest cogging torque is conventional stator. When the motor have high torque, and the speed of motor will be slow. Result analysis BEP EMF. In this analysis, as you can see, the graph fundamental BEP EMF is good. Every design is good, but for the harmonic BEP EMF is not good for 2 segmented and 4 segmented because there are more distortion, and the less distortion is conventional flux switching per magnet, and the most distortion is 2 segmented flux switching per magnet. For the ammeter coil flux linkage at various armature coil density, this is our armature current density, start for 0, 5, 10, 15, 20, 25 and 30. And after that, we use formula to get the input current armature coil IA. So if you can see, after we insert the input in the circuit, we get the calculate the max flux view of all design. So we using Excel and generate the graph. As you can see, the conventional have highest maximum flux view at a value of JA30 0.078 Weber, and the lowest is 2 segmented stator flux switching permanent magnet is 0.046 Weber. We can get the average torque vs various armature current density. So as you can see, the conventional have more average torque, which is the value is 213.85 Newton meter, and the lowest is 4 segmented stator, which value is 161.83 Newton meter. So we can conclude here is the more average torque you have, the motor will be slower. Next analysis is torque and power vs speed of conventional flux switching permanent magnet. And as you can see, the blue one is a torque, the orange one is a power, and speed of 4447.52 rpm is the highest torque for conventional flux switching motor at value of 250.16 Newton meter, with higher output power at 1150.6 kilowatt, drop in output power up to 23.28% at speed of 27,700 35.17 rpm, which value 88.27 kilowatt. And for 2 segmented flux switching permanent magnet, the highest torque of 2 segmented is 182.44 Newton meter at speed 8563.39 rpm, and the highest output at 202.54 kilowatt at speed 18,032.48 rpm. Output power begin drop to 112.23 kilowatt at speed 49,081.66 rpm, which is about 44.56% drop. For the 4 segmented flux switching permanent magnet, the highest torque record is 162.72 Newton meter at speed 6682.09 rpm. For the output power, the highest is 135.69 kilowatt at speed 31,391.71 rpm. As you can see, the output power gradually decrease about 8.55% at value 124.09 kilowatt at speed 80,230.99 rpm. So for the conclusion, we can conclude that when torque is highest, the speed of motor will slower, and output power will drop when the flux switching permanent magnet motor operate beyond the base speed region due to heavy iron loss and copper loss. The conventional motor have a higher torque than other two design model that can cause the speed of motor become slower. And for the segmented flux switching permanent motor have more advantage than conventional flux switching motor in terms of electromagnetic performance overall and have flexibility. For example, if the stator core in conventional is broken down, the motor cannot be running. But if the segmented stator, one of the stator core is broken down, the other segmented will be still running. So that's all for me. Thank you.